I think we'll get started with the introduction. So welcome everyone. This is our second Munch and Learn for 2022, our 12th or 13th Munch and Learn since we started the program last year. So I'm very happy to see a good crowd today. Today we have two speakers, Neil and Alex, both from the original Determine AI company, now with HPE AI and HPC. And the topic of today is Golden Age of AI, Dark Age of AI Infrastructure. I like the title. And before I hand over to Neil, our main speaker, I'd like to go through just a few slides that maybe if you're familiar with the Munch and Learn, you've seen already, but we maintain a couple of pages that you might find useful. For Munch and Learn, we have one called Campaign Munch and Learn, and I'm pretty sure Denis from our team will drop the links in the chat for you to cut and paste. This is where we maintain our calendar of events for Munch and Learn. These are monthly. You can find the registration link, and I would say 1 week later, the replay link for the session. We have a session planned for March already for with a topic called Mithril, which is a project, an open source project, which HP is driving to build a robust identity into a service mesh such as Istio, using Spiffy and Spear for the identity management. So this is probably going to be a very interesting topic, and there will be an introduction to Spiffy Aspire, also to service mesh, and then the solution that we are proposing. So stay tuned. This is already planned for March 23rd. And if you go to the Munch and Learn page, you can find a link to register for this one. We also started a different type of talks we call meetups, a little more in-depth maybe on a particular technology. We had one session already in January. These are monthly again. You can find the page with the calendar to register in the campaign/meetup page. And we had a session last month run by Red Hat on Quarkus. And we have one coming up next week by the Streamlight people on Streamlight. And after that, we'll have one in March on vFunction. And we have also one planned in April for Open Policy Agent by a company called Steer. So take a look. The calendar for these is up already, and you can register. Remember, this is also to have fun, and we have our Munchie contest thing here going on. So if you have a Munchie you want to share, I already did mine, and you can put it on our Slack channel. You can join our Slack channel by registering on the slack.hpdev.io. Once you're there, there's a Munch and Learn dedicated channel, and that channel has a bunch of pictures like that. You can also put it on Twitter, it's okay. So share with us, it's also about fun. So don't hesitate to do that. If you're interested in joining that community, which makes sense only if everybody is engaging, we have a QR code here that you can scan with all the different channels that you can decide to join if you're more like a newsletter person or Slack or just a website. So don't hesitate to scan that code. Everything starts basically at hpdev.io, and the rest unfolds from there. So with that, I think it's a great time for me to hand over to Neil for the real content of the session. It's all yours, Neil.
Perfect. Thank you, DJ. Okay, perfect. Let me just share my screen. Okay, perfect. Everyone see that?
Yeah.
Great. Well, thank you everyone for attending. This talk is on, title is Golden Age of AI, Dark Ages of AI Infrastructure. My name is Neil Conway. As one of the founders of a company, Determined AI, where we spent the last almost 5 years building infrastructure for cutting-edge teams doing AI, deep learning at scale. And we joined HPE back in June of last year. And in this talk, I'm going to talk about, main focus is going to be areas where we see opportunities for improvement in AI infrastructure. I think the basic thesis is that AI represents a new set of challenges, a new way of building software, a new way of building applications, and we've started to see some of the promise of that of AI in terms of enabling new applications, but the infrastructure, our software development tooling, has really not caught up. So yeah, so that's gonna be the talk. So let's get into it. So, first of all, golden age of AI, I think it's, hopefully it should be relatively easy to make the case that we are really seeing machine learning start to realize the promise that it's had for a long time. A new kind of family of machine learning methods that people call deep learning have developed over the last few years, training massive models on clusters of GPUs and leading to a real step function improvement in the ability of machine learning to solve really challenging problems. Particularly in computer vision and natural language processing, we're seeing whole new kinds of applications that simply wouldn't be possible without the latest advances in machine learning. And I think we're only scratching the surface. Self-driving cars, computational drug discovery, virtual assistants, GPT-3, and I think it seems like every week there's another application of AI that emerges that is really exciting. Oh, and just an aside, if folks have questions, please post in the chat. I'll kind of pause periodically and check if folks have questions, but there should also be plenty of time for discussion and Q&A at the end. So if we're in the golden age of AI infrastructure, I think the reality, though, is that most organizations still really struggle to equip their ML engineers with the tools that they need to be productive and successful. And that is, in my view, a major bottleneck to more widespread adoption of ML and success with ML. So this talk will be structured around 4 vignettes talking about really practical problems that teams that are ML engineers face today, trying to build AI-powered applications, and how those challenges are met by today's generation of tools. And I think talking about some of the opportunities for improvement. So the focus is not going to be on the solution side. I think talking more about opportunities here. But I will include a brief plug for some of the ideas around what we've built and a little bit of an idea about kind of how software that we built in the past kind of relates to some of the challenges that we talked about. So before we start talking about the vignettes, I just want to take a step back and talk briefly about what a typical workflow looks like if you are an ML engineer building training models, doing ML model development today. So you start with a business problem that you think is going to be well solved by machine learning. And you start collecting data, you build a data set that you think is relevant to solving that problem. And then you start to find or to look for models that you think will work well on that data set and enable you to a useful model that solves your problem effectively. So that might involve taking starting with an off-the-shelf model architecture, maybe something developed by Google or Facebook or some of the other leading research groups. That it might involve custom model development, or starting with an off-the-shelf model, then doing a bunch of tweaking and tuning. But that's very much an experimental process of exploring hypotheses, looking at different data sets, looking at different model architectures, training those models, doing what's called hyperparameter tuning, which you can think of as model optimization, and then repeating this process, iterating, exploring more ideas, collaborating with other people on your team. Ultimately, once you get to something that is that you think is going to work well for your application, then you need to deploy that model to wherever it is that you want your model to be operating. That might be a smartphone, might be a web service, might be somewhere on the edge. So throughout this, you're also working with large data sets, so you need to think of a data management, and you're also working with massive compute clusters. So you need to think about, how do we manage that infrastructure? How do I apply that infrastructure to the workloads the work that I'm trying to do? And I think talking about AI infrastructure, there's a lot of excitement around tools like PyTorch and TensorFlow. And those are kind of really focused on that inner loop of model training. So solving that problem of, how do I write down my model architecture, the way that I'm optimizing my model, the way I'm loading my data, and how do I translate that into operations that run on my GPUs. Those tools, I think, really start with enabling a single ML engineer to train a single model using a single GPU, and that that workflow actually works really well, and that's improved a lot over the last few years. But I think where you often start to see challenges emerges when you start to think about operating at scale, or operating on, how do I collaborate with my team? How do I manage larger, computational resources? How do I tune and optimize my models? How do I keep track of all the models that I'm training over this process? So that's kind of a brief overview of the kind of what's involved in training a machine learning model. And now I think, I want to turn to a few vignettes of, once you've kind of gotten through that day one, ML on day one, let's say you follow the PyTorch tutorial, the TensorFlow tutorial, you train a well-known model on a public data set using a single GPU. Then on day two, you take on a bunch of additional challenges as you start to operate at larger scale, train a custom model, use more resources, work with a larger team. So we're going to talk about 4 vignettes of situations where, where a hypothetical person takes on some of these day 2 challenges, and how they, how the current ML infrastructure that we have enables, what problems that the current tooling solves, and what problems remain pretty challenging. So let's start with training models using multiple GPUs. So let's talk about our hypothetical friend Dave. Dave's a smart ML engineer, and we talked about ML being applied to some of the most important problems in society. So let's take a absolutely critical problem. How do we generate better beams? So Dave does a bunch of research. He comes up with a brilliant model for generating better memes and doing what's called style transfer based on some of the cutting edge techniques in ML modeling, what generative adversarial models, GANs. And the model looks really, really promising. He reads a great research paper about it, so he goes and trains it on his data set. And he waits and he waits and he waits. Turns out, even using the latest generation of GPU, it takes a month of compute time for that model to finish training, which is not actually that surprising. One of the kind of consistent, it's been true for the last basically 10 years now, that the computational requirements for state-of-the-art models in ML have been doubling approximately every 6 months. So when you think about 10 years of much faster than Moore's law growth, the computational requirements of state-of-the-art models now are really pretty incredible. So Dave goes to his boss and says, "Look, generating better memes is crucial to the business. We need more compute infrastructure." So obviously they think, well, okay, HP Apollo 6500s, let's get a cluster of those to enable our ML team to be more effective and have the resources that they need. So they get some Apollos, they've got plenty of GPUs. So Dave's problem solved, right? He has a very computational intensive problem, and now he has a lot of GPUs. Well, how does Dave actually apply multiple GPUs to speed up model training? So that's there are various techniques to solving what's called distributed training, or training a single model using multiple GPUs at the same time. I won't go into the details. One of the most popular and I think generally applicable techniques is called synchronous data parallel training. Essentially, you split up your data set, you train parts of the data set on different GPUs, and then the GPUs coordinate in order to simulate, to get the same behavior as if you train the entire model on a single GPU. This enables the GPUs to work together and to get the same results. So there's many tools for doing distributed training. You may have heard of tools like Horovod, which are originally developed by Uber, DeepSpeed from Microsoft, BytePS. Their methods built into TensorFlow and PyTorch. So again, is this problem solved? We have multiple GPUs. We have an algorithmic technique for using those GPUs to train our model more quickly. And we have software that implements that technique, right? So is that problem solved? Well, it turns out that there's a pretty big disconnect between those tools and those algorithms and actually enabling Dave to get his work done more quickly. So the first challenge is Dave needs to modify his model code. So he already has code that works great for training us on a single GPU. And he needs to modify that code to essentially call into some of these tools like Horovod or DeepSpeed or the distributed training in TensorFlow and PyTorch. And it's fairly easy to to write code that is supposed to run on every GPU and actually runs on one GPU or vice versa. It also means you end up having two code paths. You have one code path for when I'm using multiple GPUs and another code path for when I'm using a single GPU. So it's a very common source of bugs. It's easy to to kind of make a maintenance mistake to make a change to one code path but not to the other. But Dave's a smart ML engineer. Let's suppose that he figures all that stuff out. So next you need to install a bunch of kind of complex dependencies, kind of these libraries for high-speed communication, things like MPI, nickel, glue, and so on. Okay, you got to make sure those are all consistent across all the machines you're training on. Okay, that's fine too. You need to configure your network because these frameworks are passing massive amounts of information over the network. Let's suppose that Dave does all that. It's annoying, but it's not the end of the world. Okay, so first of all, Dave does all this stuff, and then, how is he even sure that the results of training a model with using one GPU or using many GPUs is the same as training on a single GPU? As we talked about, because he has to modify his code, it's very easy to make a mistake and to do something on one GPU when it should be done on all of them, or do it on all of them when it should be done on one GPU. So algorithmically, you should see exactly the same behavior using many GPUs with synchronous training as a single GPU, but in practice, it's very common for discrepancies to arise. And these are the kind of things that are difficult to debug because in machine learning, in classical software, we have a very it's easy to understand what correctness means, right? You have some kind of specification where we have a spec that we're programming against. We know the kind of behavior that the program should exhibit. With the machine learning task, it's much more empirical. It's much more of kind of the scientific process where, it's not clear a priori. If I train a model, it exhibits certain behavior. Is the multi-GPU case, if there's a discrepancy, which behavior is correct, right? There's a lot of kind of debugging and empirical work that I have to do to kind of figure that out. But Dave again is a very sharp guy. I suppose that he kind of figures out all these challenges. So now he has multiple machines and lots of GPUs, and he needs to launch a task on all of those machines to make sure that they're coordinating, collaborating to train this model. So he's a machine learning engineer, never particularly done that before. So he says, okay, well, I know how to use SSH. Let me kind of hack up some scripts on top of SSH and launch process on all the machines. So he does that, he's excited. He's fixed all his convergence bugs. He's written his training script to launch jobs on the entire cluster, and he kicks off a new multiple GPU training job. But it turns out he doesn't see any speed up at all. So then he debugs and he tries to understand what's going on. Turns out that he hasn't even thought about data yet. All we've been talking about is parallelizing compute. And if he doesn't think about where my data lives, how it's going to get to all these GPUs in a high performance way, it's often the case that you won't see a significant performance speed up. So then Dave says, okay, well, I guess I need to use a distributed file system. So he goes and, installs one of those and configures it. The way that I'm loading his data probably needs to change as well. So he goes and sits down and does that. And then finally, after going through all of this work, Dave sees, is eventually able to see a significant speed up in model training performance. Keep in mind, that's not the end of the story, right? So all we've done here is enable a single person to train a single model using many GPUs at once, right? If other people join Dave's team and they want to share and collaborate on that GPU cluster, if he wants to burst to the cloud and add new capacity to his on-premise cluster, if he wants to explore using new kinds of ML accelerators like other kinds of GPUs or custom ML accelerators from companies like Cerebras and Habana, those are all very reasonable things that Dave might want to go do. But again, his infrastructure provides very limited help there. He's going to have to sit down. He's going to have to change his code. He's going to have to do a bunch more infrastructure work. So I think, the observation here is that on the one hand, modern ML makes utilizing massive compute resources, that really does need to be table stakes. For many teams, that's very important to be able to apply, more than one GPUs to your problem in order to enable your ML engineers to make progress quickly. And a lot of the work that Dave has done has really nothing to do with machine learning, right? It involves infrastructure management, it involves writing boilerplate code, it involves configuring networks, installing MPI. And really all Dave wants to do is use multiple GPUs here. If you compare that to, let's say using parallel compute with a framework like Spark or Hadoop or a modern data warehouse, a business user writes a SQL query and they don't have to think about how that query is parallelized or where the data is stored, or if they add an index to their database, they don't need to rewrite all their application logic. Whereas Davis kind of repeatedly had to sit down and install new infrastructure or modify his code or really account for, he needs to change his workflow to account for the fact that he's just using a different number of GPUs. So I think, for me, there's a couple observations there. One, the need to modify your code when your infrastructure changes is really something that should be a last resort. If to me, it suggests that the way that we're writing down our model code is there's something that should be improved there, because Dave's model architecture hasn't changed. The ML problem that he is trying to solve remains exactly the same. All that's changed is that he has changed the infrastructure in which he wants to run that workload. So being able to separate the properties of his model, the high-level machine learning tasks that he wants to solve, from the infrastructure in which that problem is running, is an important property for systems in this space to have. And the second is that, if you ask someone, well, how do you do distributed training of a deep learning model? I think a common answer would be to say, well, you use a tool like Horovod or use a tool like DeepSpeed. And that's true. Those are exceptionally good tools. They deliver high performance distributed training. They, for some definitions, they solve the problem of distributed training. But I think, as we've talked about, there's still a really big gap between these tools that claim that they solve distributed training and actually enabling a team of ML engineers to be able to apply multiple GPUs to a problem in a routine way over the course of their work. So, these tools like Horovod and DeepSpeed, you can think of them as kind of very narrow and very technical, right? They're very focused on the minutia of parallelizing the training problem and doing high-speed network communication, which are certainly important challenges. But there's there's a whole raft of other problems that teams need to tackle if they really want to enable their ML engineers to be able to make use of large-scale compute in a flexible way to get their ML work done more quickly. So maybe I will pause here and just check if there's any questions before we go on to the next topic. Great question about how can distributed processing help Dave's problem. Hopefully the content I talked about, hopefully that makes that clear. And there's the whole algorithmic side of how do you take training a deep learning model and how do you parallelize that efficiently. I haven't covered that at all. There's plenty of work on that. That's an active topic of research. Some models parallelize well, other models you're going to see less of a speed up, but there's a whole kind of other set of concerns which are more practical and I think in practice are still a challenge for a lot of teams. Perfect. Awesome. Okay, so that's those are some of the challenges that Dave runs into if he wants to use multiple GPUs to train a single model. And now let's talk about fault tolerance. Okay, so Dave's figured out how to use, he's got a GPU cluster, he's figured out how to use multiple GPUs to train a model more quickly. And he's reduced the time it takes to train this model from a full month down to only 2 days, right? So I think it's worth observing that if you told this typical software engineer that take you 2 days to compile compile your software project, they would look at you like you were, you had two heads. But for some areas of machine learning, that's kind of typical to see that kind of training performance. So Dave is able to kind of apply a lot of compute to train this model much more quickly than he otherwise would be able to. But the next problem he runs into is that whenever there's an error, let's say that there's a transient network error, or one of the machines runs out of memory, or there's a disk space error, or a process crashes. Whenever there's an error, the entire training job crashes, and there's no fault tolerance. We have to restart, Dave has to restart his entire job from scratch. So that's pretty frustrating, right? Dave was training this model for a reason, in order to answer some kind of question, explore a hypothesis. Every time that happens, Dave loses, on average, a full day of his time, plus hundreds of hours of GPU compute, which is also pretty expensive. So this makes Dave really frustrated. So what can he do to ensure that his training is fault tolerant? Well, so fault tolerant computing in general can be pretty complicated. It involves complicated stuff like Paxos and Raft and two-phase commit and Byzantine fault tolerance. But if all we're doing is training a machine learning model, this should be relatively simple, right? So it's a read-only task. We are just launching a bunch. We're doing kind of a batch computation. And we just want to restore the state of that computation if any of the workers involved in the computation crashes. So simple technique, checkpoint restart. You basically take a checkpoint of the state of your computation periodically. And then if there's a crash, you kill off all the workers, you restart everything, and you restore it from the most recent checkpoint. Might not be the most efficient, but it's should be relatively simple and should enable us to tolerate faults while we're training models. And in fact, deep learning frameworks like TensorFlow and PyTorch have checkpointing built into them as one of the core things that they're doing. So if we're using TensorFlow Keras, we call save model, and then so Dave modifies his code to say periodically save a model to his distributed file system, and then if there's a crash, he writes some code to reload the model using load model and to resume training. So problem solved, right? Well, not quite. So first of all, checkpoints for these frameworks typically only include some of the information that you would need to make your computation fault tolerant. So basically, a bunch of the state of the training algorithm, what are called the model weights, the architecture, the state of the optimizer, those are captured by a checkpoint. But where you were in the data set, the random seeds that you used, the model definition itself, those are not captured in a checkpoint. Very easy to forget this kind of stuff because fault tolerance is kind of like backup, in that these are code paths that only get exercised when something goes wrong. So Dave probably doesn't realize this the first time, and then there's another crash and his model doesn't train the way that it was supposed to because it restarted and it was the wrong place in the data set, or didn't use the right random seeds. So Dave eventually realizes that. It does a much more debugging. Okay, so he writes some more code to save that additional information and make sure that it's restored properly. So problem solved. Well, again, not quite. So it turns out that these models are pretty big. Taking a checkpoint on one of these models might be hundreds of megabytes or a gigabyte. And Dave, writes some simple code to just take checkpoints and store them. He's training many different models. Turns out that he runs out of disk space fairly quickly. So, okay, so he says, okay, fine, that's annoying. I'll set up PagerDuty. I'll, write some cron jobs to delete model checkpoints that I probably don't need anymore. Maybe write some kind of monitoring script to keep track of the models that I'm training. So he continues to make progress. But at the end of the day, again, Dave has finally been able to make his model training process fault tolerant, but he's really had to do a lot of manual work, right? He's had to reinvent a bunch of infrastructure that arguably should have already existed. And again, he's spending time on tasks that really have nothing to do with machine learning. They're infrastructure management. They're writing boilerplate code, and the support that he gets from his infrastructure, again, is just the ability to save a model checkpoint, right? From TensorFlow's perspective, they've enabled fault-tolerant training because they allow you to take checkpoints. But there's really, again, a pretty big gap between that kind of basic feature of save a checkpoint and load a checkpoint and what Dave needs to enable him to train models without losing a bunch of work if there's a transient fault. So Dave had better infrastructure, this really wouldn't even be something he'd have to think about. The infrastructure would take the checkpoints automatically. It would check for failures, and if a job failed, it would kind of automatically manage the process of finding the last checkpoint, restoring the work, making sure that all the right information in the checkpoint is being saved and restored, and it would manage all of Dave's storage, right? Rather than requiring him to understand these are checkpoints that are really important that I need for a production model, and these other checkpoints are just kind of temporary checkpoints that I created for fault tolerance reasons. The system would kind of manage all that checkpoint storage automatically. And again, here, looking at the way that databases work, or looking at the way that other systems work, it's enabling fault tolerance without requiring the users to think about how that fault tolerance is implemented and manage their own storage is really, I think, would be a massive productivity improvement for ML engineers. Okay, let me just pause quickly. Perfect. Okay, so no more questions at the moment. So let's go on to the third example. So this is what's called model tuning or hyperparameter tuning. Okay, so Dave has a script for training his model, as we've talked about, but it turns out that Dave's model, performs pretty well, but it doesn't perform as well as the state of the art. So, the state of the art memes are really compelling. They're really funny. Dave's memes, they're not bad, but they really need to be better in order to be competitive with a very, very competitive meme generation market. So what should Dave do? Well, there's a bunch of approaches you could take as a data scientist here. You could say, well, maybe we don't have the right data, or maybe we have the right data, but we're not representing it in the right way. Maybe we need to use a different model architecture. But a common activity here would be to what's called tune hyperparameters. So the hyperparameters of a model you can think of as they're basically characteristics of the model that aren't trained by looking at the data. There may be characteristics of the training procedure itself. So they're sort of, you can think of this kind of configuration settings on the model. And there's not really typical deep learning models might actually have quite a few of these configuration settings. 10, 15 is not uncommon. So if you think about, suppose that we have 10 or 15 hyperparameters, and each one might range from, might take on, let's say, 100 possible values. That kind of 10-dimensional or 15-dimensional space, it represents a huge number of possible model configurations, each of which might have different performance. So, and because these hyperparameters can really have a very significant impact on the performance of the model. So this forms a pretty challenging search problem to kind of explore all these configurations to find the one that yields the best model performance for Dave's data set. Especially because evaluating a single one of those configurations, training a model to convergence on a with a single set of hyperparameters configurations, might take 2 full days. So if you think about, let's say 10 to the 15 data points, and fully evaluating any one of those data points might take you 2 days of computation, it's a very expensive search problem to kind of solve exhaustively. So Dave says, okay, well, I want to improve the performance of my model. Can I find some better hyperparameters that yield better performance? So, what's the first thing you might do? Well, in this case, let's say Dave selects two hyperparameters that he thinks are the most important, what's called the learning rate and the dropout. And, we write some nested for loops in Bash, right? So we say, okay, we'll look at a bunch of different learning rates, we'll look at a bunch of different dropout percentages, and we'll just train our model on every combination, every crosswise combination of those two hyperparameters. So, I mean, that works well enough. But the problem here is that all of a sudden we've gone from training a single model a single time on a single GPU to training now tens or hundreds of models. So before we had a single log file, that model had a single set of metrics that described it. It had a single model checkpoint. Now we have hundreds of checkpoints, hundreds of log files, hundreds of model metrics. And it's up to Dave to basically comb through all of this metadata and figure out, well, of the 100 or 200 models that I just trained, which one is the yields the best performance? How do I kind of preserve the checkpoints for that model, preserve the metrics for that model, make sure I write down the hyperparameters that actually got the best performance, and how do I discard the rest of that information? Not only that, but Dave's for loops run sequentially, right? So he's training one model at a time. In this case, if training a single model took 2 days, we might easily be training 100 or 200 models. That's doing that one after another is going to take an infeasibly long amount of time. Dave says, okay, well, let's install a cluster manager. Let's train all these models in parallel, right? Let's use Slurm or Kubernetes or something like that. So Dave, goes back to his trusty for loops and launches all these jobs so they train in parallel. So that does, that does give him a speed up. All of these workloads are kind of totally independent. They could be trained in parallel. But now Dave has even more log files and even more metrics. And part of the challenge here is that the cluster manager, the workload scheduler, has no idea that these workloads are related to one another. Right. So Dave can't see the progress of his search. The search itself isn't fault tolerant. So if Dave's shell crashes, he loses all of his work. As far as the cluster manager is concerned, you've just launched a couple hundred training jobs that are kind of completely unrelated to one another. So, I mean, looking at the problem that Dave is trying to solve, I think, there's two kind of shortcomings. One, he is trying to perform a task for which he doesn't have good infrastructure support, right? His search strategy is basically for loops in Bash. And those the jobs that he's submitting to the underlying cluster manager, there's no that doesn't have any understanding of the actual task that Dave is trying to accomplish, because it's just a generic cluster manager, a container orchestrator like Kubernetes or Slurm or what have you. Doesn't have any fault tolerance, doesn't have any way of organizing all of the metrics and artifacts that get produced by throughout this process. And obviously, you can think about ways that you could optimize the work that Dave is doing from a system point of view in terms of caching data or amortizing common work across all of these common models that are being trained. The other kind of shortcoming here is that Dave's search strategy is, really not that intelligent, right? He's exploring every possible combination of hyperparameters, whereas, it's very likely that certain values of those hyperparameters would be very easy, very quick to determine that don't result in good model performance, and we could kind of prune those parts of the search space. So how could we do better? Well, it turns out there's actually been a ton of research into intelligent algorithms for hyperparameter tuning. Hyperband is an algorithm, that is one of the state-of-the-art approaches that, one of my co-founders of the company, his lab, were one of the folks who developed. But, the intuition there is basically that you pick a bunch of these configurations at once. So you randomly sample from the hyperparameter space, and you run each model for a very short period of time, and you prune the configurations. You basically kill off the configurations that aren't doing well and start more randomly chosen configurations. And the configurations that are doing well, that seem to have good performance, you allocate more resources to them and you train them further and further. So there's a lot more math behind that kind of basic intuition, but it turns out that for a wide class of models, this is a very kind of effective technique in terms of very quickly finding model configurations that perform well. So, okay, here we have hyperband. It's yields very good kind of model performance, and that Dave's for a model, Dave's able to quickly get to a model that a hyperparameter configuration that performs well for his problem. But why is it difficult for Dave to apply hyperband to his problem? This is a relatively simple algorithm. I just gave you the intuition for it. And you can, find scripts on GitHub that implement it and kind of similar hyperparameter algorithms. But, one challenge for Dave is, first he's got to adopt yet another special purpose tool, right? So we needed to adopt a different tool for distributed training, a different tool for tracking Dave's experiments, a different tool for hyperparameter search. And a lot of these implementations of hyperband are not really production grade. There's a lot of them are kind of only work on a single node, or they have very limited interaction between the search algorithm and the cluster manager. Because if you think about what this algorithm is doing, it's exploring all of these configurations, and you want to be able to kind of prune interactively. So you want to be starting many things at once, stopping the ones that aren't working well, allowing the ones that are working well to continue running. You want kind of a lot of interplay between the individual workloads and the and kind of the search algorithm itself, which is something that's going to be challenging to do with a if you just view this as launching a whole bunch of independent batch jobs. And the kind of reality is that despite the fact that hyperparameter tuning is a pretty common activity for ML engineers, and that there's been years and years of research and literally hundreds of papers written on more efficient hyperparameter search algorithms, most practitioners today still use fairly simple methods with very limited tool support. So this idea of nested for loops is actually surprisingly common in practice. And ML engineers will often have kind of an intuition for where they feel like the kind of interesting parts of the hyperparameter space are. But this is not something where it's not like if you're writing software and you turn on optimization in the compiler, and the compiler automatically produces a faster executable. This is very far from that in practice. Most folks, it's much more manual process, much more ad hoc, for which tool support is still not widely used, and these more advanced search algorithms are still relatively rarely used in practice. And what's part of the challenge here, right? In that the tools that Dave is working with he has a cluster manager, but that doesn't understand anything about machine learning or about the actual task that he's trying to solve. And he has these deep learning frameworks like TensorFlow and PyTorch, which really focus on training a single model for a single user on a single machine. And I think what's kind of missing is the infrastructure that enables that. It's kind of the missing glue that extends those deep learning frameworks to account for the cluster in which they're running, the resources in which they're running, and the end-to-end workflow that Dave actually wants to accomplish. So I'll just pause here. So this is a good question. Justin is asking, based on this, is the idea of a citizen data scientist an impossibility? So I guess the way this talk is structured, it makes it sound like I'm very, I have a very pessimistic view, and I don't think that that's not kind of the reality. I think I'm kind of just highlighting opportunities where ML engineers could be better served by better software. And the other point here is that I think there's room for a lot of tools here, right? So what we're talking about are relatively sophisticated users who are training custom models from scratch. So these are folks at the, working on pretty sophisticated applications. So think of, the people training computer vision models for self-driving cars, or the people building state-of-the-art language models, to, things like GPT-3 and so on. I think there's plenty of room for data science more generally, folks who are just trying to analyze business data, and that's a pretty different problem. Or for off-the-shelf vision APIs, off-the-shelf language APIs, making it easier for for teams to get reasonable performance on well understood problems using using kind of well-known modeling techniques. I think, you know, so there are, in terms of kind of citizen data scientists and so on, I think there's plenty of opportunity to build better tools to enable those citizen data scientists to be more effective without requiring them to understand the nuances of either machine learning or kind of large-scale compute infrastructure. But I think, you know, the focus of this talk is on for those teams who are building cutting-edge machine learning applications, for those ML engineers who understand tools like TensorFlow and PyTorch, who are building, you know, modern computer vision, modern NLP models, who understand statistics. How can, you know, what are opportunities to build better tools for those teams to be more productive and for them to really focus on doing machine learning? Because I think one of the kind of common threads in the kind of examples I've talked about is, you know, you have these ML engineers who at the end of the day are trying to solve machine learning problems. And the state of their tooling today means they end up spending a lot of time on infrastructure management, on writing boilerplate code, on you know, setting up cluster managers and distributed file systems, and, you know, dealing with a lot of complexity that you know, is ultimately caused by their choice of tooling or the state of the tooling, rather than you know, what they'd prefer to do, which is really kind of focus on machine learning and focus on building better models for the problem they're trying to solve. Great. So there's a question about how companies like Facebook, Amazon, and Google are handling some of these challenges. Yeah, I mean, I think these are challenges that those organizations face. And, you know, I think that is one, and they, you know, places like Google, Facebook, Amazon have internal infrastructure that handles a lot of these challenges. Talk to people at those companies, and I think they'll say that infrastructure is not perfect, but it's definitely, these are challenges that those organizations are aware of, and they've made a major investment in solving. So I would say we're sort of in a situation where right now teams face a couple alternatives, right? Either you don't invest in building that infrastructure and you don't invest in building that ML platform, and then, as we're talking about in this talk, your ML engineers often have to spend a bunch of time compensating for the lack of that platform, the lack of that infrastructure. Or if you're at one of these handful of kind of elite organizations that have the scale to justify building these internal ML platforms, and, you know, we're talking about teams with you know, hundreds of software engineers in some cases, then that's, you know, that's a very significant investment. But I think it's a relatively small number of places that can justify that investment and kind of operating the scale where that's something that they want to go do. So I think there's a real opportunity, and, you know, that's something that have been trying to do at Determined, is to kind of think about how to solve some of these problems in a more generic way, in a way that is widely reusable between companies. Because I think a lot of these challenges that we're talking about are not specific to particular industries or particular companies, but are kind of widely encountered by teams that are doing cutting-edge machine learning. Yeah, and I think, so a question from Andrea about how HP can help our customers with these challenges. Yeah, I think that's a great question. You know, I think at HPE, I think we're really well positioned, because if you think about what do teams need to be successful to do modern machine learning, right? I think, you know, certainly they need data, certainly they need people with, you know, who understand machine learning. From an infrastructure point of view, they need massive computation, they need storage, they need networking, and then they need a software layer that really enables those ML engineers to utilize that compute infrastructure. So I think there's an opportunity for you know, I think enabling that compute, storage, and networking to be approachable to ML teams, connecting that to the challenges ML teams face, and then really building software infrastructure to utilize those resources effectively and to enable teams to go much more quickly from acquiring those compute resources to actually applying them to ML in practice. I think that's where the right software and the right ML infrastructure really comes into play to enable to kind of make that a much shorter, more direct kind of process of going from hardware resources to actually more efficient ML teams. Perfect. So I have kind of one more anecdote around what's called reproducibility, and then I'll just wrap up. Okay, so let's continue with Dave. So he solved this meme generation problem, let's say, and he and now he moves on to a new project. So one of Dave's former colleagues, Leslie, she trained a production model for, let's say a computer vision task 6 months ago. Leslie got poached by one of their competitors. She's no longer at the company, and Dave's task is take Leslie's model and explore whether we can improve its performance. So if you were asked to do that, what's the first thing that you do? I think, I would start with saying, well, can I reproduce the behavior that Leslie observed, right? So Dave starts by taking Leslie's training script and retraining, a new model, which in principle should behave exactly the same way that Leslie's model has in the past. Turns out that that's not the case, right? That Dave retrains Leslie's model, but it actually results in much higher error and much lower accuracy. So he, he says, okay, well, I've got to debug this problem. So he starts digging in and he discovers, well, first of all, Leslie trained her model on different data. So more data has been collected. Maybe that data is represented differently, has different properties. That's one reason why the model's performance was different. Second, as we talked about, hyperparameters can have a big influence on model performance. Turns out Leslie didn't use the default values of those hyperparameters. She kind of specified a few of them at runtime when she trained the script, and hopefully she wrote those values down somewhere. And Dave's able to find them, maybe on a wiki page or in a README file somewhere, and use the kind of correct hyperparameters. So Dave makes those two fixes, and he sees much better performance, right? So we saw about if the baseline is 30%, he started with around 50% error. He now gets down to around 37% error. So he's definitely making progress, but there's still a big difference between the model that he's training and the model Leslie trained previously. So he says, okay, more debugging. He thinks, what could be going on? What's the problem? Well, it turns out that using pseudo-random numbers is a very commonplace part of training a deep learning model. So the way that weights are initialized, the way that the order in which you look at the data set within the network itself, randomly, pseudo-randomly generated numbers are kind of used throughout that process. And, if you don't fix the seeds of those random number generators, you're going to get different random numbers on every kind of training line. So Dave says, oh, okay, so I got to fix my random seeds. It's a bit more complicated, different frameworks have different random seeds and there's a bunch of them, you've got to write them all down, but Dave fixes that problem. He's also got to keep in mind, well, different versions of different software dependencies can have different statistical behavior, cuDNN, CUDA, and so on. So he says, okay, well, I'll use containers. I'll set up a container registry. I'll kind of standardize my training environment. I'll make sure that I'm using exactly the same versions of all these frameworks and dependencies that Leslie used. So non-trivial to get that right, but Dave sits down and does all that work. Now he runs the script again, and he's much closer, but he still is not able to reproduce the results that Leslie observed. Now, what could possibly be going on here? And Dave gets pretty frustrated, but then he realizes, well, actually, the training process itself can be non-deterministic, especially running on a GPU. The order in which floating point operations are done, and some of these underlying packages like cuDNN will choose different algorithms in a non-deterministic way in order to improve performance. So Dave says, okay, that's a little frustrating. These tools kits don't provide reproducibility out of the box, but he kind of reads through a bunch of documentation, figures out how to set some obscure environmental variables, and his training process goes a lot slower, but ultimately he's able to get reproducible training. So had to run on the CPU, couldn't use a GPU, had to disable a bunch of the performance optimizations, but in the end of the day, he is able to get reproducibility. And again, so this is something where being able to reproduce the work that someone else on your team has done is really a pretty fundamental requirement, right? As software engineers, we think about, a colleague of ours does some work, it's in a branch on Git, we check it out, we build it, and it's, we're basically assuming that we're going to be able to reproduce their work if we're going to collaborate. That's kind of one of the kind of basic building block for us to be able to work together and make progress, is being able to reproduce the work that other people on our team have done. But as we can see, this is really not something that Dave gets out of the box, or that a tool like TensorFlow gives you out of the box. And there's a bunch of these additional kind of considerations that Dave has to think about, has to account for in order to get reproducible machine learning. So, it's not that it's not possible by any means, but there's a lot of stuff that you've got to get right, a lot of, a bunch of different fiddly little factors that you've got to make sure that you don't, mistakes that you don't make in order to get reproducibility. And again, I think there's an opportunity here for frameworks and for infrastructure to take on reproducibility as one of the kind of core kind of properties that we want to preserve, rather than something that is kind of an afterthought, and something that you can get it if you want it, but it's something that is kind of on the user to account for all those variables. So those are the 4 vignettes I want to talk about. I think, I just want to wrap up quickly by talking about, what are some of the kind of common threads. So I think, if you look at the tooling that Dave was using, I think there's a lot of it tends to fall into 2 buckets. Some of those tools are too generic in that they're built without an understanding of machine learning, things like cluster schedulers, for example. Machine learning, it just is a pretty different workload, and the challenges that machine learning teams face, I think, are pretty different than traditional workloads like data analytics, or even lighter weight data science. But then when you look at some of these specialized tools that are built for modern machine learning, tools like TensorFlow or Horovod, they're often very narrow in that they focus on solving these very narrow technical challenges without thinking about the end-to-end the end-to-end challenges that as an ML engineer that you face. So if you think about TensorFlow, it does checkpointing. Checkpointing does, is one of the ingredients towards building fault-tolerant training infrastructure. But there's a pretty big disconnect between the ability to take a checkpoint and having all your workloads run without having to worry about fault tolerance. So I think ultimately we need, infrastructure that is specialized for machine learning, that accounts for the different properties that machine learning has compared to other, more classical kinds of computing, but still thinks about the end-to-end workflow that ML engineers need to go through in order to get their jobs done. And I think that opportunity of thinking more broadly and thinking about taking a holistic approach to the challenge that ML engineers face gives us the opportunity to build fundamentally better tools, and tools that really enable ML engineers to be much more productive. So to kind of wrap up, a lot of the tool, a lot of the challenges that Dave's facing are not exotic, right? These are really pretty essential capabilities after you think about kind of going beyond some of the most basic, once you've trained a single model on a single GPU, you're rapidly going to run into some of these challenges. And I think there's a real opportunity for tooling to do better, to more directly enable Dave to be successful. So quick plug, Determined, and at HPE, we're building a model development environment that includes a bunch of these capabilities built in. It does GPU management, it does built-in distributed training, it tracks all your experiments, it has built-in hyperparameter search, makes it very easy to get reproducibility. And we've tried to follow that philosophy of thinking about ML engineers, what are their workflows, and what's the right way to build software support for those workflows. So think we're at time. I will kind of wrap up. I'm happy to kind of continue to take any questions from folks who have them. Thank you so much for your interest. Hopefully folks found this interesting. I think Alex will post a few links in chat to Determined if you're interested in checking it out. It's all, open source. We have an open Slack. We would love, if there's kind of some of the challenges that I've talked about are familiar, or you think your team might run into them soon, would love to talk more about that and see whether Determined might be a good fit. So thank you so much for everyone's attention.
Thank you, Neil. That was great. Thank you for your time. Thank you, everyone, for joining. Sorry for being 1 minute late. I think that was a great discussion with Neil. Thanks, Alex, for answering the questions in the background. We'll talk to you in 1 month. Thank you very much, everyone.